Ladies and gentlemen, my name is Maria Konstagdoudos. I would like to thank you very much for inviting me. My favorite city here at Hong Kong. I have visited Hong Kong 3 other times, Gordon conferences, and I have to say that I would never say no to a trip to Hong Kong. It's really such a beautiful, marvelous city. Thank you very much to my good friend here, Professor Lang from HCAST. I have the opportunity of being here with you guys. This is a great opportunity of discussing new issues, new matters, and concrete technology. Having said that, my goal today is to show you a few aspects of concrete nanotechnology, and not only what nanotechnology can do in structures, modify structural properties, but also I will give you a small glance at the self-sensing properties that we can achieve by using nanomaterials. Let me move to the side, and maybe that would be even more helpful for you seeing those slides here. Chris asked me earlier, where exactly is Arlington? And I told him, I explained to him, I'm going to give you just precisely where Arlington is. University of Texas at Arlington. Obviously, University of Texas is at Texas. And there is let's say, a series of University of Texas, the most famous being University of Texas at Austin. And there is a University of Texas at Dallas, but Dallas is a small, the University of Texas at Dallas is a small university. The basic university is the University of Texas at Arlington, which is right in the middle between Dallas and Fort Worth. And Dallas and Fort Worth are known as the Dallas and Fort Worth Metroplex area with a huge airport, the DFW, as we call it. And actually, I was so happy to find out that DFW has a direct flight from Dallas to Hong Kong. So here is Arlington and can be considered a suburb of either Dallas or Fort Worth is right in the middle, and DFW is right here, 15 minutes from the University of Texas at Arlington. Arlington is also famous of building a few years ago the AT&T Stadium, and AT&T Stadium is a major stadium for all the major sport football events of the United States. So University of Texas at Arlington thrives for excellence. It's a Carnegie type 1 university, high research activity. The graduate students are highly diverse. We have students from all over the world. It is the fastest growing doctoral public institution of the United States, only because Texas is one of the fastest growing, let's say, states of the United States. And besides that, it's also the second largest state after the state of California. So moving on, I've recently joined the University of Texas at Arlington 6 months ago, not even 6 months, maybe 5 months ago. And my role at the University of Texas is not only to be a professor of civil engineering there, but with Professor Shah, we established the Center for Advanced Construction Materials. And the Center for Advanced Construction Materials is a university center. It doesn't belong to any department, but it's being supported by the Department of Civil Engineering and Material Science and Engineering. And its goal is to develop and test innovative and engineered smart materials for the infrastructure. Just going to show you a few of the projects that we are starting with, rather than we are continuing with. Development of nanomodified cementitious materials with improved mechanical performance, design, characterization, and implementation of multifunctional and self-sensing materials, formulation of admixtures, experimental, analytical, multi-scale characterization of complex fluids, and advanced engineering materials. This is another sophisticated expression of describing 3D printing and self-consolidating materials. We need that multi-scale characterization of complex fluids, meaning fluids at the very early stage of concrete, and exploring electrochemical and surface and interface phenomena at all scales with focus on durability, especially on corrosion of steel in concrete. And we are trying to evaluate the state-of-the-art, let's say, at the interface of steel and concrete when concrete matrix is nanomodified with different nanomaterials. So the center, the director of the center is Professor Shah, and we just hired 2 new assistant professors, Dr. Ashraf and Dr. LaPlante from University of Maine and from University of California, Los Angeles. We do have 1 postdoc, and we are looking for more postdocs. Feel free to recommend postdocs if you have some, and we are accepting doctoral students and master students if they are willing to come to the United States. We have purchased all this piece of equipment here, atomic force microscopy, though the materials department of UTA has almost everything, yet we needed a few advanced let's say, state-of-the-art piece of equipment like this particular one, 3D computed tomographer, and rheometers with Raman capabilities. So we are well equipped, and we are looking forward to work on new projects, like projects from Texas DOT, and Texas Department of Transportation is one of the, let's say, biggest and richest Department of Transportations of the United States. So I think I skipped a slide, and I skipped just a small, let's say, I'll give you a hint about the topic of my talk today, high modulus concrete, and I'm sure you know better than me why high modulus is very important to structural engineering. We are looking into new building designs, reduced footprints to ensure occupant comfort. This is the goal when we are trying to find out how we can increase the modulus of elasticity. And everything for us started a few years ago when we started talking with Thornton and Tomasetti. Thornton and Tomasetti is the company who built Trump Tower in Chicago and several other high-rise buildings. And I think that now Thornton and Tomasetti is building the Kingdom Tower. And the only reason I'm showing you Trump Tower is because Thornton and Tomasetti requested a modulus of elasticity of 44 gigapascals, but at the compressive strength of only 83 megapascals. And this is exactly what Thornton and Tomasetti is doing right now for the Kingdom Tower, obviously using the local materials there, aggregates and stuff. And I think what they wanted is keep the same compressive strength and increase a little bit the modulus of elasticity up to 45 or 46. Now you are going to tell me what's 1 or 2 gigapascals, but 1 or 2 gigapascals at this particular range of concrete is too much, too high. So in order to do that, Thornton and Tomasetti, actually it was Prairie who designed the concrete, used a water to cement ratio of 0.28, too low. Microsilica, fly ash, slag, fine aggregates, coarse aggregates, but everything was local in Chicago. Now, for the Kingdom Tower, the problem was that 0.28 was not even pumpable at the 1 kilometer height that the Kingdom Tower is about to go. It hasn't finished yet. It will finish soon, but the builders wanted to find a way of increasing the modulus, but without increasing the compressive strength. And this is a problem that is kind of unusual, because is there a way of increasing the modulus without increasing the compressive strength of concrete? If you look at all the relationships, and here I have a nice curve that was prepared by Zongjing Li, and it gives us a compressive strength relationship with a modulus of elasticity, especially for high-strength concrete for tall buildings. And that was one of his projects, and it was developed as a final report in 2016, I think, but this one was also presented at a conference back in 2014. So look at these special mixes here, A, B, C. A, B, C, for example, have a water-to-cement ratio of 0.28, like the Trump Tower, 0.23, and 0.20. And in order to have a modulus of elasticity higher than 45, we have to increase the compressive strength higher than 110 MPa. And this is how it goes all over the world, actually, because this is the only way of increasing the modulus of elasticity. Another way of increasing the modulus of elasticity, besides lowering the water-to-cement ratio and include silica fume and all this supplementary cementitious material, is use stiffer aggregates. But then again, even if we use the stiffest aggregate possible, for example, here, the crushed quartzite, then we can increase the modulus of elasticity using a water-to-cement ratio, 0.26 here, and then the modulus that goes, let's say, up to 48. Still, we do not have the desired increase that materials people envision at this particular moment. Silica fume can do the magic, gives us a higher modulus of elasticity, but at the same time, it can give us a higher compressive strength, and most important of all, it gives us a high propensity for autogenous shrinkage cracking. So no matter what we try, and I can show you the previous slide again, all these mixes contain silica fume. And actually now, the modern form of silica fume would be nanosilica right now. But still, whatever we try, we cannot have the advantage of a high Young's modulus with a reasonable, moderate, let's say, compressive strength. If we include nanomaterials in concrete, that gives us, let's say, a partial solution to our problem. And the reason I'm saying partial solution is because nanomaterials are very difficult to work with in terms of their dispersion. Before we, let's say, draw any valid conclusion, we have to make sure their dispersion is successful, because only when, for example, carbon nanotubes, when are dispersed uniformly, can reduce the fiber-free area of the material, and we have an effective load transfer. So unless we know about the dispersion of the nanomaterials, we are reluctant to draw any conclusion in terms of the properties that we are examining. A very good dispersion procedure these days is with the use of ultrasonic energy, and the use of ultrasonic energy is by far the best method of dispersing well any nanomaterial that we use, not only carbon nanotubes. And what we want to make sure is that we do not use any surfactants to functionalize the material other than the usual surfactants that we use for concrete. For example, superplasticizers. So in this particular method that we developed 3 patents with Professor Shah, we are using ultrasonication and the regular surfactants that we use when we are making high strength and ultra high strength concrete. And it works actually quite well for us. And you can see here, effective dispersion for us means that there is nothing on the walls, that it's stuck on the container walls. Obviously, this is just an optical, let's say, method, just what we see in situ. If we want to check the dispersion, we have better ways of checking it. For example, we use UV-vis, ultraviolet visible spectroscopy, and we are able to establish a relationship between the peak of the light that is being transmitted in our dispersions and the energy that is provided to the dispersion, so that we can have an effective dispersion and not have breakage of the nanotubes or the nanofibers inside the mix. Providing higher energy than the necessary, then we saw that we are cutting the nanotubes in half, and this doesn't work to our benefit. So what we can achieve by using carbon nanotubes and carbon nanofibers in concrete? Actually, carbon nanofibers are even better than carbon nanotubes in terms of the structural properties, because they are longer and they are giving us an advantage of a fiber. While carbon nanotubes sometimes can be really small and they are not giving us the advantage of a fiber, they are giving us an advantage of a nano particle. So here you see the Young's modulus of concrete, say regular concrete, which is with and without carbon nanotubes. Here is with carbon nanotubes, 0.1% per weight of cement. This is an extremely small amount of nanomaterials. If you translate it in the volume of concrete, it doesn't even alter the, let's say, the cost of the material, maybe by $5 to $10 per cubic meter, similar to when we are, let's say, when we are making high-strength concrete. So you see both modulus here, compression and tension of concrete specimens, concrete with carbon nanotubes and concrete with carbon nanofibers, and we can almost double the Young's modulus of the concrete with carbon nanotubes and carbon nanofibers by using just 0.1%. The interesting part here is that we can double the modulus. We can double the flexural strength. From 6.7, we can make it almost 10, but we do not see any effect on the compressive strength of concrete. The amount of material is so small that it doesn't give any change in the compressive strength of concrete. We search into that, why we see that huge, let's say, increase in modulus, and we were able to identify through nanoindentation that carbon nanotubes can increase the high stiffness CSH of the cement paste. And see here, the normal cement paste, the neat cement paste, is about 15 to 20, the Young's modulus. And then with carbon nanotubes, through the reinforcing effect, we can increase it from about 20 to 30 gigapascals. And that was the one step that we took in our early research. Later, we were able to identify that the Young's modulus was highly increased at the interfacial transition zone. Similarly, in a similar way that we have observed so far with the silica fume. And those silica fume is giving us adverse effects like high shrinkage cracking. Carbon nanotubes do not give us any of those adverse effects. So with QNM, quantitative nanoscale mechanical characterization, and by designing a simple experiment, and you can see here the images from the atomic force microscopy. Here is the aggregate. We were able to identify the interfacial transition zone here and measure the modulus of elasticity, which is in absolute agreement with the results that we see at the macro scale. So back to the fact that we can increase the modulus, but we do not increase the compressive strength. We've done a series of experiments, and we've tested many types of concretes and mortars, plain with carbon nanotubes, carbon nanofibers, and in different proportions of carbon nanotubes and nanofibers. And we were able to see that the higher proportionality of the stress-to-strain curves indicates a higher load carrying capacity in the elastic area. We were able to see the same effect in all our mixtures. And actually, we were able to identify the first crack strength here, which is the first point that from a stress-strain curve, the curve deviates from the proportionality that we want to see in the elastic stage. And we were also able to identify the first crack strength and the first crack toughness. And the first crack toughness is an indicator of the ductility of the material, of the energy absorption capability of concrete, only that we are still in the elastic area. We haven't moved into the post-cracking, let's say, area after the concrete moves after the first crack. We double-checked our experiments with 4-point bending experiments, only to find out that the concretes with 0.1 carbon nanotubes, the nano-reinforced concretes, are giving us flexural toughness that is, let's say, 47, about 50% higher. And what you see here is a comparison between fracture mechanics tests and 4-point bending tests. The only thing that I want to show you right here is that 4-point bending tests have a disadvantage of giving us results that are size dependent. Fracture mechanics tests are giving us results that are not size dependent, are size independent. And Professor Lang will remember with me Professor Bazan's theory about the size dependence of the problem that we face with size dependent specimens. But if you look at this, we have completely different values of the energy absorption capability, only that the percentage of the increase is the same. The values are different because we have size dependence, but the increase, regardless, is the same. So toughness indices, and because they notified me that I have only 5 minutes to go, I just want to move quickly back to the results that we took from your work, guys, here, from the tall buildings that they were designed here in Hong Kong. And only in this graph, we included the Hong Kong code, and we included also the Euro code, and also the ACI codes. So 2 curves, Euro code and ACI codes, and the Hong Kong code, and then These are the empirical, let's say, relationships established for so long between compressive strength and modulus of elasticity. And we can clearly see that if we want to satisfy Thornton and Tomasetti's requests to increase the modulus of elasticity higher than 45 gigapascals here, the only way to do it is if we design a concrete with 100 MPa compressive strength. And actually, this was our concrete as well. That was a concrete with 0.51 water to cement ratio, and a concrete with 0.32. And all of our concretes were within the limitations, the limits here of the Euro codes and the Hong Kong code. But when we design concrete with carbon nanotubes, here is the concrete with water to cement ratio 0.5, and this is giving us, let's say, a 46 Young's modulus. And here is the concrete designed with water to cement ratio 0.32, and it's giving us a 48 Young's modulus. Compressive strengths no higher than 65 MPAs. So yes, we were able to satisfy Thornton and Tomasetti. Actually, we were able to satisfy also the requests for the pumpability, and the mix is highly pumpable. But still, we are looking for the opportunity of Thornton and Tomasetti to, let's say, they want to build a nice, let's say, balcony in a building in Milwaukee first before they tried it in a, let's say, tall building like this. I am going to finish my presentation here, and I can show you later on in individual discussions, if you want, the opportunities of the self-sensing ability that carbon nanotubes and carbon nanofibers can provide in, when are used in concrete. What I'm showing to you here is two curves. One is the stress-strain curve. The blue is the stress-strain curve. And the red curve is the piezoresistivity curve, as we call it. And the piezoresistivity curve is actually, you can see how the material here, the specimen here, fails along its loading. And this is mortar. We have the same exact curves in concrete. And look at the two curves, they are like mirror image curves. We can discuss this later if you want, because we do have nice results. We can use the same mortars as sensors inside concrete elements, structural elements, and we do have the exact same results as I'm showing here. And I'm gonna finish my talk showing to you what we are working on at this particular time. Strain sensing ability for structural health monitoring. We are examining corrosion, and we have found out that carbon nanotubes delay the onset of corrosion of steel and concrete. We are doing de-icing applications for DFW because DFW wants, let's say, to Minnesota is doing this with carbon fibers, but we are doing this with carbon nanofibers. So we are creating the so-called smart pavements. And finally, this is a project that I have started while I was working back in Greece, a European Union project. How about if we are able to harvest the excess thermal energy and transform it, convert it into usable electrical energy? Thank you very much for your attention.